Hi everyone, welcome back to my videos. I'd like to do a tutorial on chords and congruence. So theorem 1, we're given a circle of center O. We're given that segment OM is perpendicular to segment AB, segment ON is perpendicular to segment CD, and segment OM is congruent to segment ON. Prove that segment AB is congruent to segment CD. So what we're proving here is if two chords in a circle are equidistant from the center, then those two chords are going to be congruent. So I write down what I know. And I know the perpendicular segments meet at right angles, right, from what we have in 2 and 3. So angle OMA is and angle ONC, they're both right angles, and therefore they're congruent because all right angles are congruent. We know that segment OA and segment OC are both radii, right? Because they're both segments joining a point on the circle with the center of the circle. And so segment OA is congruent to segment OC. We can apply the hypotenuse leg postulate using what I have in 5, what I have in statement 7, and what I have in statement 4 to get a triangle OMA is congruent to triangle ONC. Therefore, segment MA is congruent to segment NC. So if you look at what I've drawn, I've actually extended segment OM to the point to where it actually intersects the circle. Same with segment ON, I extended it to where it actually intersects the circle. So we can be rigorous and say if a radius is perpendicular to a chord, then the radius bisects the chord, right? If I just included OM and if I didn't extend it, I couldn't really apply that theorem to say that, M is a bisection point, N is a bisection point. So anyway, given that, so we know that 2 times segments MA is going to be congruent to 2 times segment NC, right? By the multiplication property of congruence and what we have in statement 9. And then using the fact that point M and point N are bisection points and therefore they're midpoints, right? So segment MA, the length of this is going to be, if you do 2 times this length, you get the length of the full segment AB. And if you do 2 times the length of NC, you get the entire length of CD. So segment AB is congruent to segment CD. Okay, theorem 2, in a circle of center O, segment AB is congruent to segment CD. Segment OM is perpendicular to segment AB, and segment ON is perpendicular to segment CD. Prove that segment OM is congruent to segment ON. So here we're given 2 chords in the same circle are congruent, and we want to prove that they're both equidistant from the center of the circle. So write down what we know. We know that segment OA is congruent to segment OC. All radii of the same circle are congruent. Segment OB is congruent to segment OD, same reason. And I'm going to apply side postulate using what I have in statement 2, statement 5, and statement 6 to get triangle OBA is congruent to triangle ODC, and then angle OBA is congruent to triangle ODC by corresponding parts of congruent triangles are congruent. We know that angle OMB and angle OND are right triangles because perpendicular segments meet at right angles in what we have in statement 3 and 4. And all right angles are congruent, so angle OMB is congruent to angle OND. We can apply angle side postulate to what I have in statement 8, statement 9, and statement 6. So we get triangle OMB is congruent to triangle OND, and therefore segment OM is congruent to segment ON. By corresponding parts of congruent triangles are congruent, so we proved what we wanted to prove. Let's do problem 1 here. Given segment AD is perpendicular to segment BC, segment FE is perpendicular to segment AB, segment FG is perpendicular to segment AC, and we have a circle of center F. Prove that segment EF is congruent to segment GF. So we write down what we know, and we know if a radius is perpendicular to a chord, it bisects the chord. So segment FD bisects chord BC. So I extended segment FD to where it intersects a circle, so we can actually say, this radius actually bisects segment BC, and we'll just take, segment FD, which is technically the subset of the radius, but, we just want to know that D is the midpoint, right? So, we know that angle ADB and angle ADC are right angles, right? Because perpendicular segments meet at right angles, given what we have in statement 1. And all right angles are congruent, so angle ADB is congruent to angle ADC. I'll use the reflexive property of congruence to get segment AD is congruent to itself. And we know that segment DB is congruent to segment DC, because to bisect a segment is to divide it into two congruent segments. So we can apply side angle side using what we have in 8, what we have in 7, and what we have in 9 to get triangle ADB is congruent to triangle ADC. Therefore, segment AB is congruent to segment AC. We can just read that off from what we have in 10. And we know that segment AB and segment AC are both chords of the circle, right? In both cases, we have a segment that joins 2 points on the circle, and that's the definition of a chord, right? So we know if 2 chords are congruent, then they're equidistant from the center of the circle. Well, what is segment EF and segment GF are both, they represent, the measures of these represent the distance from, the chords to the center of the circle. So we know that segment EF is congruent to segment GF. Okay, so problem 2, we're given that segment CD is congruent to segment CE. Segment CD is perpendicular to segment AO, and segment CE is perpendicular to segment BO, and we're dealing with a circle of center O. Prove that triangle CAB is isosceles. So I write down what I know. Segment AO is congruent to segment BO. Why? Because segment CD and segment CE are both chords of the circle, right? And if chords are in a circle are congruent, then they're both, equidistant from the center of the circle. We know that angle CAO and angle CBO are right angles because perpendicular segments meet at right angles, and we know that from what we have in statement 3 and statement 4, and therefore angle CAO is congruent to angle CBO because all right angles are congruent. We know in a triangle if angles are congruent, then sides opposite those angles are congruent. So if we look at statement 5, we're given segment AO is congruent to segment BO, right? So these angles here, angle OAB and angle OBA are both congruent, right? And then I can use the subtraction property congruence to what I have in statement 7 and statement 8. And then if I substitute, I get angle CAB is congruent to angle CBA. We know in a triangle if 2 sides are congruent, then the angles opposite those sides are congruent. So it's like what we did in statement 8, but kind of like the reverse, right? So segment CA is congruent to segment CB. And we know a triangle if at least 2 congruent sides is isosceles. So triangle CAB is isosceles. So this last problem is challenging, but let's not be intimidated by it. Let's just go over it step by step, and it won't be so bad. So we're given a circle of radius O. We're given segment AB is congruent to segment DE. So these are chords, right? Segment AB and segment DE. And we want to prove that segment BC is congruent to segment EC. So we write down what we know, and I'm going to draw a radius OM and ON. So between 2 points, a line and hence a segment can be drawn. And we know that segment OP is congruent to segment OQ because if chords of a circle are congruent, then they're equidistant from the center of the circle. And we know that chord AB and chord DE are congruent. We know that segment OP is perpendicular to segment AB and segment OQ is perpendicular to segment DE. Why? Because these are just the distance from the center of a circle to a chord is measured on a segment that's perpendicular to a chord, right? So this is the segment that's perpendicular to a chord, and the same with OQ, right? It's perpendicular to the chord DE. We know that angle OPC and angle OQC are right angles because perpendicular segments meet at right angles, and all right angles are congruent, so angle OPC is congruent to angle OQC. I'm going to draw a segment OC connecting O with C, and I can do that because between 2 points a line and hence a segment can be drawn. Remember, segment is just a subset of a line, right? So, and I'll use the reflexive property congruence to get segment OC as congruent to itself. I'm going to use the HL postulate using what I have in 8. You know, all these right angles are congruent, right? What I have in 10 and what I have in 4 to get triangle OPC is congruent to triangle OQC. Remember, the HL postulate only works when you're dealing with a right triangle, right? We know that it's a right triangle because we have right angles. So segment PC is congruent to segment QC by corresponding parts of congruent triangles are congruent. Okay, so we know that P is the midpoint of segment AB and Q is the midpoint of segment DE, right? Because if a radius is perpendicular to a chord, it bisects that chord, right? And OM is a radius and ON is a radius, right? So it's gonna bisect chord AB, DE, right? And the midpoint is the point that bisects the chord, right? So we know that the length of PB segment is going to be 1/2 times the length of segment AB, and the length of segment QE is going to be 1/2 of the length of segment DE. Therefore, by the definition of segment congruence applied to what I have in 2, we know that length of AB is equal to length of DE. And if I do properties of equalities and multiply this by 1/2 on both sides of this equality, we get what we have in 17, right? And then by properties of equality, we know that PB is equal to QE if I combine what I have in 14, 15, and 17. So by the definition of segment congruent, segment PB is congruent to segment QE. And therefore, by the subtraction property of congruence, segment PC minus segment PB is congruent to segment QC minus segment QE. By substitution, segment BC is congruent to segment EC, which is exactly what we want to prove. So that's all I have for you today on chords and congruence. I hope you enjoyed this video. More importantly, I hope you learned something from it and you got something from it, because that's the purpose of these videos, right? So go over some of the stuff we've done before and kind of work out the problems, and I hope to see you during my next tutorial. So have a good night, everyone. Take care. Bye.